Welcome back. We are learning about the circuit analysis using the Thevenin theorem, and we are solving the examples that contain basically dependent and independent sources. Okay, we did one example in the last video, okay, where we have basically a dependent voltage source and an independent voltage source, and we find out the Thevenin equivalent circuit. So let's solve another example. So this is a circuit. Again, the question is to find the V naught. Okay, so what we can do, we can take basically the load, which is basically what, okay, we can take basically voltage drop here. So again, this will be open circuit, so we can take both of them together and take it outside of the circuit as our load. Okay, so this is 1k, this is 2k, and our target is to find V naught. Okay, because it contains a dependent sources and independent. Okay, so we need to calculate basically our Thevenin and open circuit voltage V Thevenin. Okay, our Thevenin will be what? V Thevenin divided by the short circuit current. Okay, so to get the V Thevenin, we need to make this point open. Okay, so let's redraw the circuit with that case. So this is plus minus 3 volt. I have 6k here. I have 2k here with the current Ix here, and I have a dependent source plus minus 1000 of Ix. I have a current source here which is basically 1 milliampere. Okay, and we want to find basically what is the voltage drop here. That will be R Thevenin. To get the short circuit current, we will redraw the circuit again. Okay, so minus 3 volt, 6k, 2k, and this is a current Ix. Then we have a dependent source with 1000 Ix, and I have a current source with the value of 1 milliampere, and we make here a short circuit branch. Okay, so this is our short circuit branch here, and we want to find out what is the current basically going through this. Okay, so this is our target. Okay, well, let's do it step by step. Let's first calculate the V Thevenin. Okay, so to calculate the V Thevenin, again you can use different techniques, but I'm going to use the node here because nodal analysis will make the quicker. Okay, because see, I can find a super node here, right? A voltage source between the two nodes, right? So let's define the voltage at the node to apply the nodal. Okay, so we can say that this is V1, let's call this V2, and let's call this V3. So V3 is basically your V Thevenin, right? Because this is the voltage drop across 1 milliampere source, so that will be basically V Thevenin. Alright, let's write that super node equation first. So that will be V2 minus V3 is equal to 1000 of Ix. And what is Ix? Ix is the current through this one. So what is Ix? V2 minus 0 divided by 2k, right? So 2k means 2000, right? So let's put that here. So I can write this as 1000 times V2 over 2000. Okay, so that will be cancelled. Okay, so we have V2 minus V3 is equal to V2 over 2. Okay, or this can be written as V2 minus 0.5 of V2 minus V3 is equal to 0. Okay, or 0.5 of V2 minus V3 is equal to 0. Okay, so this is our first equation. Okay, so like 1 minus 0.5, it will be 0.5. All right, now let's write the KCL equation. So this current, what will be that? V2 minus V1. What is V1? Minus 3. So minus 3, that will be plus 3 divided by 6k. This current, that is what? V2 minus 0 divided by 2k. Then, okay, this node current, that will be basically minus 1 milliampere is equal to 0. Okay, so we have two nodal equations. Okay, this one and this one, two unknowns. We can solve them to get the value of V2 and V3. Okay, So if we solve that, the value of V2, okay, it comes out to be basically 3/4. Okay, so V2 will be 3/4 volt. Okay, and the value of V3, which is basically our Thevenin, it comes out to be 3/8 volt. Okay, so we have our Thevenin here. Okay, so we got this thing. Now let's try to calculate the short circuit current. Okay, now again here, if you look at this circuit, what we can do here. Okay, so again, like if we try to apply the nodal here, okay, so nodal will like we can apply the nodal, we can apply the mesh, whichever technique that seems better to simplify this one, right? So actually what will happen again here, because this is the short circuit, this is in parallel with this 1 milliampere. Okay, so this 1 milliampere, the whole current, okay, when it comes here, that will basically will go to the other side, right? Okay, so this whole current will go to the other side. It means no current will be flowing basically towards this side, because this is the short circuit, right? Current always follows through a short circuit path. So if the no current is flowing through this one, it means Ix is 0. So if Ix is 0, it means this voltage drop here, 1000 times of this one, this will be 0, right? So if this whole thing become like this one, okay, so our circuit basically will become more simple, right? So what will be our circuit here in that case? Okay, so like this become 0, right? So 0 means no current is flowing here. So this is again a short circuit, right? Okay, because all the current is basically going to the other side. Okay, so our circuit will become more simple. Okay, and that circuit will basically look like this one. Okay, so Ix is 0, no current is flowing, actually open circuit here, so minus 3 volt. Okay, we got our 6K here. Okay, and this is no current, basically open circuit, and this is basically 0 volt, so basically short circuit. And we have this current source here, which is 1 milli, and we want to find out basically what is this current. Okay, so what will be these currents? Okay, so because of this one, okay, so we can simply, for example, apply the current divider and voltage divider here. Okay, so for example, if we just apply the nodal here, okay, so nodal will give me the voltage here, or like we can write simply the super mesh here, or we can do the source transformation. For example, if I do the source transformation, like this is minus 3 and 6, I can make this a current source, right? So what will be that current source? Okay, so that current source value will be minus 3 divided by 6, so minus 1/2, right? So I have a current source with a value of minus 1/2 milli. Then this 6K, it will come in parallel. Then we have this 1 ampere current source, and then we have this short circuit here, right? So basically these two current sources we can combine. So 1 minus 1/2, it will become basically 1 milli, 0.5, right? So and then that 0.5 current directly will be flowing through basically this short circuit. So we can say that basically short circuit current is 0.5 milliampere. Okay, so what we did here, I convert this voltage source to a like source transformation current source. Okay, so I will be 3 divided by 6 minus 1/2. Then 6K will come in parallel here. Then I combine, okay, this two current sources here. So this is like 1, this is minus 1/2. So 1 minus 1/2, it will become 0.5. Now that 0.5 will basically go through the short circuit point. Okay, no current will flow through 6K actually. Okay, So we can say that basically I short circuit comes out to be 0.5 milliampere here. So once we have this thing, we will come back to our main equation. So Thevenin is how much? 3 over 8. Short circuit is 0.5 milli, okay, or 1 over 2, okay. So that will come basically 3 over 4, okay, K, okay. So Thevenin will be 3 over 4K. Now we can simply apply the voltage divider here to get the V out. So V out will be 2 divided by 2 plus 1 plus 3 over 4K times the input voltage, which is basically 3 over 8K. Okay, so this equation is this simple equation can be simplified to get the actual output voltage. Thank you so much.